Okay, in lesson 6.5, we're going to move into 3 space. So we talk about R2 as 2 space and R3 as 3 space. Today we're going to be talking about algebraic vectors as well. So we're going to be taking our vectors and placing them onto a coordinate axis, which is just our, like what we're used to is our XY plane. And now we're going to be adding a third dimension as well. So R2 is the XY plane with real numbers going in 2 different dimensions, and the origin in 2 dimensions is at, we usually call it O for origin, and it's at 0, 0. So again, what we have here is something just like this with our X and our Y. And the first number in this system tells me my horizontal movement, and the second one tells me my vertical. And that's really just because someone decided to put Y on the vertical axis and X on the horizontal. And someone decided to put the horizontal number first. And so what we have to do in 3 space is decide what the order is for these 3 numbers. And in 3 space, what we're going to be looking at is having a vertical axis, a horizontal axis, and then we're also going to have the vectors shoot out of the page towards you. Now that's hard to draw on the internet, but we're going to add this axis here, and I want you to imagine that here it's heading back behind the computer screen, and here it's shooting out towards you. And we label these 3 axes with an X, a Y, and a Z. So this time, instead of, we're going to actually move things all around, and X is going to represent the depth now. The Y will now be the horizontal axis. And the Z is the vertical axis. Now, this representation you will see change depending on the textbook that you're using or the software that you're using in real life. So sometimes they will change which one they're calling X, Y, or Z. Our textbook uses this orientation, and it's more common in high school. Now, the values that we're using along these axes for the numbers are all going to be part of the real number system as well, just like we usually deal with in 2 space up here. The origin in 3 space is 0, 0, 0, so it means I'm not moving forward or backward, right? This first number would be my forward-backward movement. I'm not moving side to side, and I'm not moving up or down, so no movement at all. I'm starting here at the origin. All right, there are many different planes in R3 or 3 space. In 2 space, there's only one plane, and it is the plane that's created by these 2 axes. A plane is a flat 2-dimensional surface that extends infinitely in both dimensions. So I want you to imagine like a sheet of cardboard laid on top of these, or a sheet of paper laid on top of these 2 axes, but that sheet of paper is never ending. It just keeps going in all the different directions. That would be a plane lying, and sometimes we call this the Cartesian plane because it's just the X and the Y. In 3 space, however, there are many different planes. We can imagine them lying in many different directions. So I'm just going to flip over. I've got a couple of pictures here that I want to look at. So here in 3 space, they've drawn in this green plane, and this is what we call the XY plane because it lies on top of the X and the Y axis. But you could also imagine this piece of paper or this plane shifting up and sitting, 2 units higher or 2 units lower. So somebody could draw a plane up here or a plane down below it. And again, these planes would extend infinitely in many directions. Another plane that we could look at would be the YZ plane, which is like a vertical plane that faces us flat. It lies on top of the Y axis. There's my Y axis and the Z axis. And so there's that blue plane there. But again, I can imagine this plane sliding forward or sliding backwards into infinite other planes. Those would all be separate planes but parallel. And then the XZ plane lies on top of the X axis and the Z axis. It's this red plane here, and again I can imagine it sliding left or right and creating another infinite set of planes. And here we've only looked at the planes that are parallel with a pair of axes, but there's also planes on a diagonal. throughout this space. So you can imagine just taking a piece of paper or a piece of cardboard up in real life and just tilting it any slightly different direction, and all of a sudden you're looking at a new plane. Okay, so let's go back. All right, so we've talked about planes. Next, we're going to talk about the points A, B, and C in 3 space. They have an associated vector. So if my point P ends at A, B, C, there's also a vector going from O to P. So I'm just noticing. Just going from the origin to the point P, and I can create a vector there. So whenever I have a vector in 3 space, I'm always going to take the tail and glue it to the origin. So the origin is the tail, and the point P will be the head of my vector. That means that I can take any equal vector that's floating around. Remember, equal vectors have the same magnitude and the same angle. Imagine that's on the same angle. These would be equal vectors, but if I can drag the position back and glue the tails back to the origin, then I'm going to end up with the same vector, and that's why we know that they're equal vectors. So in math, we care more we don't care about the position, so we just anchor it to the origin. I can do the same thing in 2 space though as well. We can take any vector and place it with its tail at the origin, and so we're going to call that, taking all those equal vectors that were floating around, when we glue the tail to the origin, we call it the position vector. So once I move it there, that's the name. All right, so we're going to take a look at this first example here. In the diagram, we're going to draw the vector from O to Q. Now what they've done here is they've labeled a bunch of different points in 3 space, and this example is just to kind of get us familiar with looking at 3 space or 3-dimensional space. So here I've got the point P. Now notice the point P has the 3 points, or the 3 coordinates, I should say, 0, -3, and 0. So the first one is the depth. I haven't moved forward or backward. The second one is the horizontal change. I've moved 3 units to the left. And then the third number here is the vertical change, the up or down. I have not moved up or down. So the only movement I've had is along the y-axis here. So there's point 0, -3, 0. Now m is a little bit different. It involves 2 values, 2 numbers, and so now it's no longer on an axis. So in this, to get to point m, I had to move 2 units forward. Remember, the first number is the depth, and then I moved 3 units to the left, but I did not move up or down. So there's my point. And now be careful when people draw this. Sometimes they like to, because I haven't moved up or down, they like to try to put it in line with the y-axis, but visually you have to think about moving this kind of crossbar into this corner and then moving up or down from there. So my distance vertically is going to depend on moving from here up or down. And so here I'm not moving up or down. That's why I have a 0. So from this point, if I do want to move down, say 5 units, there I would end up at point Q. Now that means that 5 units on the z-axis is actually slightly higher. So this movement here is a distance of 5 units down on the z-axis. Notice that these points do not line up, and that's because this one has also moved forward towards me, as well as horizontally to the left. So I've got a bunch of different movements here. It doesn't line up with this point here. All right, we're just going to draw in the vector O to Q here. So all that means is taking the tail and putting it at the origin, and taking the head and putting it at point Q. So I'm going to grab my ruler, and I'm going to draw my vector in, starting the tail at the origin and connecting the head to point Q. So not a difficult question here because they'd already drawn Q in for me, but we want to think about eventually you guys are going to have to draw in and figure out where that point Q is. And that's why we draw this associated box around the vector, and we're going to take a look at that in a future example. All right, in the next example here, we want to determine the coordinates of C, D, E, and F in the diagram below. Now, what we've got here are these other points A, B, and P on the box in terms of the letters A, B, and C lowercase. So we're going to come up with these in terms of A, B, and C. All right, so I would suggest that you pause the video here and see if you can figure out how did we move to get to C. You're thinking about forward, backward, and then you're thinking about horizontal, and then you're thinking about up and down. Hopefully you're going to come up with for point C here. I moved forward A units, so my first number is A. I did not move sideways from here, so once I move forward to A units, I did not move sideways to get to C. So my horizontal change is 0, but I did move up, and I moved up the same distance that this guy over here moved up. It was a distance of C. So that'll be my vertical number, my Z number. Then for D, to get to point D here, I did not move forward or backward. I did not move horizontally, but I did move up C units. To get to point E, again, I'm starting at the origin and talking about forward-backward movement. I did not move forward or backward, right? If you think about this blue dotted box here, I'm already on the back of the box when I'm at the origin, and E is also at the back of the box, so I'm not moving forward or backward. What I have done, though, is I've moved horizontally over B units, and then I had to move up C units. All right, and then our last corner is F. Again, F is on the back of the box. The origin's also on the back of the box, so I'm not moving forward or backward. But I do need to move horizontally over here, and that's going to be B units. And then I'm not moving up or down vertically, so 0. All right, our next example is example 3. We're going to consider the point 5, 2, and -3. I want to plot the point P and the related box. So watch for questions like this. Sometimes you might think that you can freehand point P, but in order for me to check your work, I'm often going to ask you to also draw the related box so I have some reference for what you were thinking. So our first job is to do some graphing. Now you're going to find I'm going to post some of this graph paper on Google Classroom so you can grab these and it's going to help out with some of our graphing. So we've got the point P. I'm just going to rewrite it down here. 5, 2, and -3. What I notice here on this graph paper is I have a distance of 5 ticks forward or backward on all of the axes from the origin. So I'm going to use a scale of 1 square for 1 tick, or 1 for 1 square, to help me plot this. Now my first number 5 is a forward-backward movement. It's on the x-axis. So when we do this, forward is always positive and backward is always negative. So I'm going to add that to my scale, that this guy back here is -5, so 1 for each tick. And this guy here is going to be +5. So always forward is positive. So when I'm drawing the box here, what I'm going to do is grab my ruler and draw a dotted line out to that 5. Okay, so first I'm moving out forward 5 units. Next I'm going to move horizontally 2 units. Now when we move horizontally, just like before, moving to the right is going to be a positive movement. So I'm going to go over 2 units. I need to add a scale to my y-axis. So again, the last tick is going to be 5, and the last tick over here will be -5. I'm not going to label everyone or it's going to get kind of messy. And I'm going to do the same for Z. Now when you're labeling the Z-axis, up is always positive and down is always negative. I'm actually going to move that negative label to the other side of the axis because I know in advance that my vector is going to end up over in this space. All right, so the third movement that I have then is to go down 3 units. So I'm going down until I get to -3 on the z-axis. So I've got my 3 numbers. Now I need to make a box out of this. So for the first 2 vectors along the x and the y-axis, I'm going to connect those 2 vectors. So you can even do this before you get into drawing the z one if you like. I'm going to connect these 2. So moving over 2 units for that one. And then moving this guy forward 5 units. And there's the top of the box. Now from each of these corners, there's 4 corners here. I need to move down 3 units. This is a measurement thing. So I need to take out my ruler and actually figure out what is this distance of 3 units. So you'll grab your ruler, you'll line it up, and I can see here that the distance is like 2.3 centimeters. And so now what I'm going to do is drag my ruler to each corner of the box and draw a line that's about 2.3 centimeters long. So there's my first one. Oops. That guy didn't work out. Okay, so now that we've drawn all the lines going down the box, oops. We're going to connect those bottom corners. So the back of the box is actually sitting at -3 on the z-axis, but the front of the box looks like more like it's like below -5, and that's okay, right? That's a perspective thing. All right, now to draw my vector in, we still haven't drawn vector OP. What we want to do is find the opposite corner of the box. So here's the origin in the top left corner, so that means that point P is going to be at my bottom right corner. There's point P, and we want to, well, in part C, it asks us to draw in this related vector. So I'm going to go ahead and do that. Oh, that's too big. When I draw in my vector, I'm starting at the origin for the tail and then ending with the head at the point P. All right, I had just written that, sorry, as a reference here. So now we have point P down here. And this red line here is actually vector OP. Now, part B asks us to describe in set notation all of the points enclosed by the box. So for part B, I'm going to say that all of the points, so I'm going to draw a set, I'm opening up the set of all the points in the form x, y, and z. But if I'm inside the box, then there's some rules for what kind of numbers I can pick for x, y, and z. So I'm going to list each of those rules. So if I'm inside the box, the x number, the forward-backward number, must be between 0 and 5. And if I'm inside the box, the y number, the horizontal number, must be between 0 and 2. And then if I'm inside the box, the z number, the vertical number, must be between 0 and -3. Oops, sorry, -3 and 0. All right. So we've already done part C here. Part C asked us to draw in that vector. That's done. Part D, then, going back up to the question, was how far is the furthest parallel face of the box from the XY plane? And that's why I had these images over here. So I have to think about, well, where is the XY plane? The XY plane sits on top of the X and the Y axis. So it's this green plane here. I want to know how far is the furthest parallel face of the box. Well, the furthest parallel face from the XY plane, I'm asking about the bottom of the box, right? Because the XY plane is the top. So first I had to figure out, right, which side was I talking about, and then which one is the furthest parallel from that. So I'm talking about this bottom, and how far is it from the top? Well, it's 3 units down. So really breaking down the question there was the hardest part of that one. Okay, part E, we're going to describe the rectangle from D mathematically. So now I want to describe all of the points that I'm going to see on the bottom of the box. So here we're asking about the bottom. Okay, so we're going to describe, there's a set of points inside that rectangle on the bottom. So again, the set of points is going to have the form x, y, z, but there's some rules for those x, y, z numbers. So to be on the bottom of the box, I'm just imagining this bottom piece. The x number, the forward-backward number, is somewhere between 0 and 5 again. The y number, again, horizontally, it's somewhere between 0 and 2, but the z number has changed. There's only one possible height that I can have. If I'm on the bottom of the box, the z number must actually be -3. So instead of writing, I could write z equals -3 here as a rule, or because it's a permanent, there's only one possible answer, I can actually write the -3 over here. It's just a little bit cleaner this way. All right, part F. Part F asks me, what is the equation of the plane that contains this rectangle? Well, if I imagine this rectangle turning into a plane, that means that the rectangle is going to spread out infinitely, forward, backward, left, and right, for eternity. And in order to come up with the points on that entire plane, there's only one rule for the points on that entire plane, and the rule is that the z number has to be equal to -3. So whenever I have a plane that is kind of looks like one of these 3 planes, where it's parallel to the planes that lie on the axis, the rule or the equation of the plane is going to look like this. It's going to be one of the variables, x, y, or z, is equal to a distance or a number, depending on how far I slid it and which axis I slid it along. So here I took this green paper and I slid it down the z-axis, so I have a z number. All right, in G, it asks us to actually repeat D, E, and F. But this time we want to do the face that's parallel to the YZ plane. So again, remembering that the YZ plane lies on the YZ axis, so it's this blue plane here. So in my picture, that's the back of the box, right? So I want the face that's parallel to that. That's the front of the box that we're talking about then. These images here off to the right, those are in your textbook. You can find those in the 6.5 section. All right, so we're going to talk about the front of the box here. I want to know, first of all, in part D, how far is it from the original plane that we were talking about, from the back of the box? Well, it's 5 units forward. And then in part E, I want to know what is the equation to talk about all the points that lie on that rectangle. And so again, I'm going to have a set of points in the form x, y, z. This time though, the x number, the front of the box, is always the same distance forward. The front of the box is always 5 units forward, but then the horizontal and vertical numbers can change. So what are the rules for those horizontal numbers? They have to be between 0 and 2. And the rule for the vertical number, the up and down, has to be between -3 and 0. All right, part F says, what's the equation of that? So again, I took that YZ plane and I slid it forward 5 units, and imagine that that plane extends. The front of the box just keeps spreading up, down, left, and right. All of the points on that plane at the front of the box would have the same x value. The x value would be 5. And there'd be no rule for the y value. It could be any number from -infinity to +infinity, and no rule for the z. It could be anything from -infinity to +infinity. Okay, the next example here, we're going to do some graphing. So again, if I were to ask you to do this on a test, I would want to see the related box. What I'm going to do is just draw some of the axes or some of the lines to lead me to these points. Okay, so I'm going to do the first one here. I want to go, and again, for all of these points, I noticed that they're between -5 and 5. So I'm going to use that same axis, -5 to 5, 5. There's my scale. All right, so for the first one here, I'm going to go, it says -3 along the x-axis. So that's -3 backwards. And then from there, I'm going to go 4 units, it says, horizontally, so 4 units to the right. And then from there, I'm going to go 5 units up. So I'm imagining, remember the 5 units has to be the 5 units along the z-axis. So you would measure that out with your ruler and then slide over and attach it to the back of the box. And then I can figure out my vector. So again, there's going to be a bunch of these guys. And you can kind of see the box here taking shape. Peace. All right, so there's the first vector, and we're going to draw it in going from O out to P. P is going to be the furthest side of the box. And so I'm going to make that one just a different color so that it stands out a little bit for you. This is going to be point P, and this is vector OP. All right, next we're going to do vector OQ. So again, I'm going to grab my ruler. And this time I'm drawing the box heading, the box in blue still. This time I'm going to go 4 units forward. The first number is my forward. And then I'm going to go 5 units horizontally in the negative direction. And then I'm going to go 3 units up. So again, I'm measuring that out along the z-axis, and then I'm going to drag that out and measure it on the other corners. And there you can kind of see the box. We're going to just connect the lines over here. You'd be using your ruler for this. And then I can see that the farthest corner of the box is here, so this is point Q, and then we'll use our ruler to connect and draw in the vector. And so there's my vector OQ. I'm going to make sure that you can see the head at the end of the vector. Oops, OQ. And I'm labeling it. All right, the next one we're going to do is OR. So we're heading out to point R. I'll grab my All right, this time we're going to go, it says 2 units is the depth, so 2 units forward. Oops. And then we're going to go from there 4 units to the right, 4 units along the y-axis, and then 5 units down. So again, I'm going to measure the 5 units along the z-axis and then drag that out. This might not have been the best color choice. So there we go. You can kind of see now the form of the box. All right, there it is. We're going to draw in our vector. It's going to the opposite corner of the box. That's going to be point R. So we'll grab our ruler. And again, starting at the origin and heading out to point R. And then I'll make sure that you can clearly see the head there at the point R. And this is vector OR. I'm going to label it. All right. The last one here, determine the equation of the plane that contains these points. So these guys are all going to be special planes. We're going to look more at planes in future chapters, but these ones are all going to be those parallel planes that are sliding with the three original that we looked at above. So I'm talking about these guys sliding forward. That's all we're going to look at in this chapter. So in this first example here, what I'm looking for is some consistency in a movement, either up or down, front to back, or left to right. And what I notice is that the left to right movement is always right 5 units. So what I have here is a plane that is parallel to this red plane. It's just slid over 5 units to the right. And so for this plane, the y value will always be equal to 5. In this plane here, it's saying pick any x and y number you want, but the z number has to be equal to 2. So this plane would be parallel to this guy here. It would just be shifted up 2 units, and so z is equal to 2. And now we're picking, actually we want the equation of the xy plane. So this one that's pictured right here laying on top of the xyz, or the xy axes. So we have to question then, what is the z value of all of these different points? Well, there is no height to them, so the z value is equal to 0. For the xz plane, we're looking at this red plane here, and again, the x value forward and back could be anything from negative infinity to positive infinity. Same with the vertical values, but the horizontal value has to be equal to 0, and so y equals 0 is the equation of that plane. All right, good luck with your homework.